Right now, a million miles away from us in the darkness of space, a machine is seeing something that should not exist. It has just spotted enormous galaxies swirling in a deep red glow, forming when our universe was only 2% of its current age. Yes, 2%. It is like discovering a fully grown adult inside the body of a newborn. Even stranger, this machine has found black holes more massive than the galaxies that host them. That is like your heart weighing half as much as your entire body, you simply would not survive. Every rule of physics we thought we understood is being broken right before our eyes. And there is one more detail that has left scientists stunned. The light this machine is collecting began its journey 13 billion years ago, before Earth even existed. It traveled across the universe for an almost unimaginable length of time, only to finally strike the lens of a machine built by human hands. What it carries is rewriting entire chapters of our cosmology textbooks. Are you ready to see the universe in a way never seen before? Secrets from the farthest reaches of space, discoveries that change how we understand the origin of everything. Hit subscribe now, because our journey back to the moment the universe was born is about to begin. Picture a machine floating in the darkness of space, 1 million miles away from Earth. That's 4 times farther than the moon. Out there, completely alone in the cosmic void, sits the most expensive scientific instrument humanity has ever built. Its name is James Webb Space Telescope, but calling it just a telescope feels like calling the Mona Lisa just a painting. $10 billion. Let that number sink in for a moment. $10 billion spent over 20 years of painstaking work. Engineers from around the world poured their entire careers into this single machine. They knew that when launch day came, there would be no second chances, no repair missions, no way to fix even the smallest mistake once it left Earth. Every single component had to work flawlessly the first time, or a decade of dreams would turn into a billion-dollar piece of space junk. The numbers tell only part of the story. To get Webb operational, exactly 1,044 different mechanisms had to unfold perfectly in the frozen vacuum of space. 1,044 opportunities for catastrophe. Each spring had to release at the right moment, each motor had to turn the correct number of times, each panel had to lock into place with millimeter precision. For 6 months after launch, teams of engineers barely slept, watching nervously as their creation slowly came to life in the darkness. One failure anywhere in that chain would doom the entire mission. The telescope itself looks nothing like what most people imagine when they think of telescopes. At its heart sits a mirror made of 18 hexagonal segments, each one coated in a microscopically thin layer of gold. Why gold? Because gold reflects infrared light better than almost any other material. When fully deployed, these segments spread out like a giant honeycomb, creating a surface about the size of a tennis court. The mirror can fold up like origami, a necessity since no rocket exists that could launch something that large in one piece. But the mirror is only half the marvel. Behind it stretches a sun shield the size of another tennis court, made of 5 layers of material thinner than a human hair. This shield doesn't just block sunlight, it creates the coldest working environment ever built by humans in space. The side facing the sun heats up to about the temperature of a pizza oven. The side facing deep space drops to nearly -400 degrees. This extreme cooling is absolutely essential, because the telescope needs to detect the faint heat glow of objects billions of light years away. Any warmth from the telescope itself would blind it completely, like trying to see stars while standing next to a bonfire. Scientists chose to park Webb at a location that most people have never heard of, something called the second Lagrange point. This spot sits 1 million miles away from Earth, on the opposite side from the Sun. At this precise location in space, the gravitational pull of Earth, combined with the gravitational pull of the Sun, perfectly balances with the speed needed to orbit. Think of it like balancing a marble on top of a basketball, except the marble is a $10 billion telescope, the basketball is Earth, and everything is moving through space at thousands of miles per hour. This parking spot offers another crucial advantage. From here, Webb can keep its sun shield pointed toward both the Sun and Earth at the same time, protecting its delicate instruments from heat while maintaining a constant radio connection to ground control. Unlike the famous Hubble telescope, which circles Earth every 90 minutes, Webb stays in roughly the same spot relative to our planet, making communication and observations much simpler. The genius of Webb lies not in where it sits, but in what it sees. While Hubble made its name capturing stunning images in visible light, the light our eyes can see, Webb operates in a different part of the spectrum entirely. It sees the universe in infrared, which is essentially heat radiation. Every object that has any temperature above absolute zero gives off infrared light. The colder something is, the longer the wavelength of infrared it produces. This might sound like a technical detail, but it changes everything. When we look at distant galaxies, we face a peculiar problem. The universe is expanding, stretching the fabric of space itself. As space expands, light waves traveling through it get stretched too, like ink on a balloon being inflated. This stretching shifts visible blue and ultraviolet light into the infrared range. The more distant a galaxy, the more its light has been stretched, the redder it appears. Hubble could only see so far because eventually, the light from the most distant galaxies shifted completely out of the visible range. To Hubble's cameras, these ancient galaxies simply vanished, as if the universe went dark beyond a certain distance. But to Webb, equipped with infrared sensors cooled to nearly absolute zero, these galaxies light up like beacons in the night. Webb doesn't just see farther than Hubble, it sees into a completely different era of cosmic history that was invisible before. The telescope launched on Christmas Day in 2021, tucked inside the nose cone of a European rocket. The launch itself was perfect, but that was only the beginning. For the next month, as Webb slowly made its way to its final parking spot, it began the most nerve-wracking deployment sequence in space exploration history. First, the solar panels unfolded to provide power. Then the sun shield began to stretch out, one layer at a time. Each layer had to separate cleanly, pulled taut by tiny motors and cables thinner than fishing line. After the sun shield came the mirror. The side segments swung out into position, then motors adjusted each one, changing their angle by fractions of a hair's width until all 18 segments acted as a single perfect mirror. Ground controllers held their collective breath through each step. There were no backups, no plan B. Everything had to work on the first try. It all worked. 6 months after launch, Webb opened its eye for the first time. Engineers aimed it at a test target, a familiar galaxy that Hubble had photographed many times. The image that came back left everyone speechless. In 4 hours, Webb captured details that would have taken Hubble weeks to see. Galaxies invisible to every previous telescope filled the background of the image, each one a whisper from the ancient universe. Then scientists pointed Webb at its real targets, at regions of space that had never been properly photographed before, at the edge of time itself where the first galaxies formed. What Webb saw in those first weeks shattered everything scientists thought they knew about how the universe evolved. The galaxies weren't just older than expected, they were wrong in almost every way that mattered. Those early galaxies should have been small, dim, and simple. They should have looked like cosmic newborns, just beginning to take shape. Instead, Webb showed scientists something that shouldn't exist: massive organized galaxies shining brightly in an era when the universe barely had time to form anything at all. Astronomers who had spent decades building theories about galaxy formation found themselves staring at data that made no sense, wondering if their entire understanding of cosmic history needed to be rewritten. When Webb opened its eye, it did more than capture pretty pictures. It opened a window into a time machine, showing us the universe as it existed over 13 billion years ago, when reality itself was still learning the rules. Every photon of light is a time traveler. When you look at the sun, you see it as it was 8 minutes ago, because that's how long light takes to cross the 93 million miles between us. Look at the nearest star beyond our sun, and you see it as it was over 4 years in the past. Gaze at a distant galaxy, and you witness history unfolding across millions or billions of years. Webb takes this principle to its absolute limit. The telescope captures light that left its source when the universe was a fraction of its current age. We're not just looking at distant objects, we're watching the universe when it was still a child, barely beginning its journey through time. In those first images from Webb, astronomers spotted a tiny red dot. Nothing special at first glance, just another faint smudge among thousands. Someone decided to run the calculations anyway, measuring how much the light had been stretched during its journey. The result made them double-check their math. Then triple-check. Then call their colleagues to verify they hadn't made some catastrophic error. The light from this galaxy had been stretched by a factor of 15. It formed just 290 million years after the Big Bang. Our universe is 13.8 billion years old. This galaxy existed when reality was only 2% of its current age. The galaxy received a catalog number, something technical and boring, but everyone started calling it Jades. For months, scientists stared at the data, convinced they must have made a mistake somewhere. Measurements this extreme seemed impossible. Galaxies this old shouldn't be visible at all, much less bright enough to show up clearly in Webb's images. They rechecked every calculation, reanalyzed every data point, looked for any error that might explain what they were seeing. The measurements held firm. This was real. Jade spans more than 1,600 light-years across. That might not sound impressive compared to our own galaxy, which stretches 100,000 light-years from edge to edge. But remember when this galaxy existed. The universe was still an infant. According to every computer simulation, every theoretical model, galaxies at this age should be tiny clumps of matter, barely organized, dim and chaotic. Jades is none of these things. The galaxy glows with the light of millions of young stars burning fiercely. It's so bright that Webb could have detected it even if it were 10 times fainter. That means other galaxies from this era are waiting to be discovered, possibly galaxies that formed even earlier, in the first 200 million years after creation. The implications are staggering. The universe assembled its first major structures much faster than anyone predicted. Scientists had built a careful story about how galaxies form. It starts with dark matter, that mysterious invisible substance that makes up most of the mass in the universe. Dark matter clumps together under gravity, forming halos that pull in ordinary matter, the gas that eventually makes stars. Slowly, over hundreds of millions of years, these gas clouds collapse and ignite, lighting up the first stars. Those stars live, die, explode, and their remains feed the next generation. Gradually, through mergers and steady growth, galaxies grow massive and bright. This process takes time. Billions of years of time. Jades didn't follow this script. The galaxy is too luminous, too organized, too large for its age. Computer simulations predicted early galaxies would be dim, chaotic, tiny. Jades radiates light from young stars, lots of them, burning bright in organized structures that shouldn't exist yet. It's not getting its brightness from a black hole eating matter, which could produce tremendous energy from a small region. This is star formation, which requires time that Jades shouldn't have had. One astronomer described the discovery as finding a fully grown adult where you expected to see a newborn infant. The metaphor captures the shock perfectly. Imagine walking into a hospital nursery and finding someone who looks 30 years old lying in a crib. That's the level of wrongness scientists felt when they saw these galaxies. Jades wasn't alone. Other early galaxies showed the same pattern. Too big, too bright, too mature. Every deep image Webb captured revealed more galaxies that violated the standard timeline. Some contained stars that had already gone through their entire life cycle, died, and spread heavy elements into space. This process should take billions of years. These galaxies had accomplished it in a few hundred million. The universe simply didn't have enough time for these structures to form through the conventional processes we understand. Gravity works at a certain speed. Gas collapses at a certain rate. Stars form, burn, and die on timescales that are well understood. Yet here were galaxies that had somehow accelerated through stages of development that should have been impossible to rush. Some scientists propose that galaxy formation happened faster in the early universe. Perhaps stars formed more efficiently back then. The gas might have been denser, allowing faster collapse. Dark matter halos might have assembled more rapidly. These ideas help explain some of what Webb sees, but they don't fully account for how extreme the observations are. The galaxies are still too massive, too bright, too organized. Another explanation involves what astronomers call initial conditions. Maybe the Big Bang didn't spread matter evenly. Perhaps certain regions started denser than others, giving them a head start on galaxy formation. These density fluctuations would act like seeds, allowing galaxies to grow faster in those locations. But this raises new questions. Why would those dense regions exist? What process during the Big Bang created them? Does this mean our theories about the first moments of the universe need revision too? A third possibility is even more radical. Maybe our understanding of dark matter is incomplete. Dark matter is invisible, detected only through its gravitational effects on visible matter. We know it exists because galaxies spin too fast to hold together without extra mass we can't see. But we don't actually know what dark matter is made of or exactly how it behaves. Perhaps dark matter in the early universe acted differently than it does today. Perhaps it clumped together faster than our models predict, accelerating galaxy formation. The discovery of jades and similar galaxies extended our view into cosmic history by 40% in just 18 months of observations. Before Webb, the oldest confirmed galaxies formed around 500 million years after the Big Bang. Now we routinely see galaxies from 300 million years, and we're pushing closer to 200 million. Each new galaxy found at these distances adds another piece to a puzzle that refuses to fit together neatly. One researcher admitted publicly that scientists built these machines not to confirm what they already believed, but to test it, to push it, to find where it breaks. They just didn't expect it to break so quickly or so dramatically. The standard model of galaxy formation, refined over decades, calibrated against thousands of observations, suddenly looked inadequate when confronted with the earliest galaxies. This is how science progresses. We build theories based on the evidence available. Those theories make predictions. Then we build better instruments to test those predictions. When the new data matches the predictions, we gain confidence. When it doesn't, we learn something fundamental. Webb's observations of early galaxies tell us that the story of cosmic evolution is richer and more complex than we imagined. But massive galaxies forming too quickly turned out to be just the opening act. When Webb turned its attention to the centers of these ancient galaxies, it found something even more bizarre. Lurking in the hearts of some of these impossibly early galaxies were monsters that broke a completely different set of rules, black holes that weighed more than they had any right to. At the center of almost every large galaxy in the modern universe sits a black hole. Not the kind formed when a single massive star collapses, those are tiny by comparison. We're talking about supermassive black holes, objects containing millions or billions of times the mass of our Sun, compressed into a region smaller than our solar system. These cosmic monsters are so dense that nothing, not even light itself, can escape once it crosses a certain boundary. Scientists have observed hundreds of these giant black holes over the past few decades. Through careful measurements, they discovered something remarkable. There's a relationship, a cosmic rule that seems to hold true everywhere we look. For every 10,000 times the mass of the Sun in stars within a galaxy, there exists roughly one sun's worth of mass in the central black hole. This ratio remains remarkably consistent. The Milky Way follows it. Nearby galaxies follow it. Distant galaxies follow it. It's one of those patterns that suggests something fundamental about how galaxies and their black holes grow together over time. The relationship makes sense when you think about it. Black holes grow by eating matter. The more gas available in a galaxy, the more the black hole can consume. But as the black hole feeds, it releases tremendous energy, heating up the surrounding gas and blowing it away. This feedback limits how much the black hole can grow. Meanwhile, the galaxy's stars form from the same gas reservoir. Both processes happen together over billions of years, naturally settling into this 10,000 to 1 ratio. This rule held true for every galaxy ever observed. Until Webb looked at the early universe. Astronomers found a galaxy from when the cosmos was only 570 million years old. They measured the total mass of all its stars. Then they turned their attention to the black hole at its center. The numbers that came back made absolutely no sense. The black hole equaled 10% of all the stellar mass combined. For every 10 times the mass of the Sun in stars, there sat one sun's worth of black hole. This galaxy broke the rule by a factor of 1,000. Scientists call it an overmassive black hole. The term barely captures how extreme this situation is. Imagine your heart weighing 1/10 as much as your entire body. You wouldn't just be unhealthy, you couldn't possibly function. The proportions are completely wrong. Yet this galaxy exists, with a black hole so massive relative to its stars that it shouldn't be possible. The problem isn't just one galaxy. Webb found more. Several early galaxies contain these monster black holes, each one far heavier than it should be for the size of its host galaxy. Some of these black holes weigh as much as all the stars in their galaxy combined. The discovery shook the foundations of black hole physics. Black holes grow by eating. They pull in gas, dust, and occasionally entire stars. As matter spirals into a black hole, friction heats it to millions of degrees, causing it to shine brilliantly before disappearing forever across the event horizon. But there's a limit to how fast a black hole can eat. Try to feed it too quickly, and the energy released blows away the incoming matter, choking off the supply. This limit, called the Eddington limit after the astronomer who calculated it, means black holes can only grow so fast. Do the math for these early galaxies, and you hit a wall. Even if a black hole started eating at the maximum possible rate from the moment it formed, it wouldn't have had enough time to grow this large. The universe simply wasn't old enough. A black hole starting from the mass of a single star would need billions of years of constant feeding to reach the masses Webb observed. These galaxies existed when the universe was less than 600 million years old. Something is very wrong with our understanding. Several explanations have been proposed, each one requiring us to rethink fundamental assumptions. The first involves what scientists call seed black holes. Maybe black holes in the early universe didn't start from collapsed stars. Perhaps they formed directly from massive clouds of gas collapsing under their own weight. These primordial black holes could have started much larger than stellar mass black holes, giving them a head start on growth. A black hole born with 10,000 or 100,000 times the Sun's mass wouldn't need as much time to reach the enormous sizes Webb observes. This idea sounds reasonable until you try to work out the details. How do you collapse a gas cloud directly into a black hole without it forming stars first? Gas clouds normally fragment as they collapse, breaking into smaller pieces that become individual stars. To form a primordial black hole, you need special conditions that prevent this fragmentation. Maybe the early universe had regions with unusually smooth gas distributions, or perhaps the first gas clouds were much hotter than gas clouds today, making them harder to fragment. These are possibilities, but they require very specific conditions that we have no direct evidence for. A second explanation involves the feeding rate. Maybe black holes in the early universe could exceed the Eddington limit. Perhaps the physics worked differently back then, allowing matter to fall in faster than our current models predict. This could happen if the gas around early black holes was especially dense or if magnetic fields channeled matter more efficiently. Some computer simulations have shown scenarios where black holes briefly exceed the Eddington limit during especially violent feeding episodes. But sustaining this superfast growth for millions of years seems unlikely. The third possibility is the most unsettling. Maybe our understanding of how black holes form and grow is simply incomplete. We've observed thousands of black holes in the modern universe, but we've never watched one form from the beginning. We've never seen a primordial black hole. We've never observed the very first generation of these objects. All our theories come from studying black holes billions of years after their formation. Perhaps black holes behaved very differently in the extreme conditions of the early universe. These monster black holes create another puzzle beyond their mere existence. Black holes don't just sit passively at galaxy centers. They interact dramatically with their surroundings. When a black hole feeds, it releases energy in the form of powerful jets and winds that can blow gas out of the galaxy entirely. This feedback regulates star formation, preventing galaxies from growing too large too fast. But in these early galaxies, the black holes are so massive that their feedback should have shut down star formation completely. Yet Webb sees vigorous star formation happening alongside these giant black holes. Somehow, these galaxies manage to form stars at prodigious rates despite having monsters at their centers that should be preventing it. One galaxy in particular stands out. The black hole at its center outweighs the entire stellar population. The galaxy should essentially be a black hole with a few stars orbiting around it, but instead, it's forming new stars at a rate hundreds of times faster than our Milky Way. The black hole is feeding, we can see the energy it releases, but somehow the galaxy has enough gas left over to create stars. This shouldn't be possible according to our models of feedback. The discovery of these overmassive black holes forces scientists to reconsider the entire timeline of cosmic evolution. Black holes and galaxies grow together, influencing each other's development. This coevolution shapes the structure of the universe we see today. But in the early universe, this relationship appears fundamentally different. Black holes seem to have formed first, or at least grown much faster than their host galaxies, dominating the cosmic landscape in ways that don't happen in the modern era. Some researchers suggest we're witnessing a transitional period in cosmic history. Perhaps the first few 100 million years after the Big Bang represented a unique epoch where different physical processes dominated. Black holes formed rapidly through mechanisms that no longer operate today. Galaxies struggled to form stars efficiently, giving black holes time to grow unchecked. Eventually, as the universe aged and conditions changed, things settled into the patterns we observe in modern galaxies. Webb might be showing us this transition, capturing the universe during its awkward teenage phase before it matured into the cosmos we know. The implications extend beyond just understanding black holes. These monsters played a crucial role in shaping the universe. Their energy output heated intergalactic gas, affecting how matter clumped together to form the cosmic web of galaxies we see today. Their gravitational pull influenced the motion of stars and gas across cosmic distances. They might have been the sculptors that carved out the large-scale structure of the universe. Understanding when and how they formed becomes essential to understanding why the universe looks the way it does. Every new observation from Webb reveals more of these massive early black holes. Each discovery adds to the mystery rather than solving it. The monsters are everywhere in the early universe, lurking at the centers of galaxies that barely have time to exist. They're growing at impossible rates, feeding on gas that should have blown away, existing in configurations that violate every rule we thought we understood. While these black holes devour matter in the centers of young galaxies, something equally remarkable happens in the spaces between stars. The universe is building its first generation of stellar nurseries, forging the elements that will eventually make planets and people possible. Every atom in your body, except for hydrogen, was forged inside a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it came from nuclear reactions deep within stellar cores. Stars are the universe's element factories, taking simple hydrogen and helium from the Big Bang and transforming them into the entire periodic table through fusion. But this process takes time. In the beginning, the universe contained only the lightest elements. Hydrogen made up about 75% of all matter, helium about 25%, with trace amounts of lithium. Everything else, every heavier element we see today, had to be manufactured one star at a time. When those stars died, especially when massive ones exploded as supernovas, they scattered their element-rich remains across space. The next generation of stars formed from gas clouds enriched by these deaths, containing slightly more heavy elements. Generation after generation, the universe slowly built up its supply of carbon, oxygen, iron, and everything else. This gradual enrichment process should take billions of years. Early galaxies should show signs of being chemically primitive, containing mostly hydrogen and helium with barely any heavier elements. Webb looked at these early galaxies expecting to confirm this timeline. Instead, the telescope found oxygen, carbon, nitrogen, and other heavy elements appearing far earlier than any model predicted. One galaxy, existing just 400 million years after the Big Bang, showed clear signatures of oxygen in its spectrum. Not trace amounts, but substantial quantities suggesting multiple generations of stars had already lived and died. Another early galaxy contained carbon in abundances that shouldn't exist for billions of years. The universe was producing heavy elements at a pace that makes no sense according to standard stellar evolution. Stars form when clouds of gas collapse under their own gravity. As the gas compresses, it heats up. Eventually, the core becomes hot enough for nuclear fusion to begin, converting hydrogen into helium and releasing tremendous energy. This energy creates pressure that stops the collapse, and a stable star is born. The star burns steadily for millions or billions of years, depending on its mass. Large stars burn fast and die young, exploding as supernovas. Small stars burn slowly, lasting for trillions of years. In the early universe, the first stars faced different conditions than stars forming today. The gas was pure, containing no heavy elements to help cool it as it collapsed. Without efficient cooling, gas clouds couldn't fragment into small pieces. The first stars were probably enormous, perhaps 100 times more massive than our Sun. These giants burned incredibly hot and bright, racing through their fuel in just a few million years before exploding violently. When these first stars died, their explosions scattered newly created elements across vast regions of space. The next generation of stars formed from this enriched material, and they could be smaller because the heavy elements helped the gas cool and fragment. Each successive generation added more elements to the cosmic mix, gradually building the chemical diversity we see in the universe today. Webb has been searching for these first stars, called Population 3 by astronomers. They would have unique properties, being made of pure primordial gas. Their light would show no signatures of heavy elements, a distinctive fingerprint that would confirm their ancient origin. Despite intensive searches, Webb hasn't found them yet. They remain hidden, either too faint to detect or perhaps completely vanished, with no survivors left from that earliest generation. But Webb has found something almost as remarkable. The telescope detected galaxies where star formation is happening at rates that seem impossibly high. These stellar nurseries are churning out stars hundreds of times faster than our Milky Way does today. The galaxies are essentially pure star factories, converting gas into stars with extraordinary efficiency. In one particular galaxy, Webb observed a region where stars are forming so rapidly that the radiation pressure from all those young, hot stars should blow the remaining gas away, shutting down further star formation. Yet the process continues unabated. Somehow, the galaxy manages to hold on to its gas despite the violent energy output from millions of newly born stars. This suggests either that early galaxies had much more gas than we thought, or that the star formation process worked differently in the early universe. The rapid production of heavy elements makes more sense in this context. When stars form at such prodigious rates, many massive stars are born. These giants live fast and die young, exploding as supernovas within just a few million years. Each explosion creates and distributes heavy elements. With thousands or millions of massive stars exploding in quick succession, a galaxy can enrich itself with heavy elements much faster than would happen in a more sedate environment like our modern Milky Way. Webb spectroscopy capabilities allow it to identify specific elements in distant galaxies by analyzing the light they emit or absorb. Each element creates a unique pattern of lines in the spectrum, like a fingerprint. Oxygen creates certain lines, carbon creates others, iron has its own distinctive signature. By studying these patterns, astronomers can determine not just what elements are present, but how much of each element exists. The data shows that some early galaxies already contain oxygen at levels reaching 10 to 20% of what we see in modern galaxies. This might not sound impressive until you remember these galaxies existed less than 500 million years after the Big Bang. The Milky Way took over 13 billion years to build up its current oxygen abundance. These early galaxies accomplished a significant fraction of that enrichment in less than 500 million years. Carbon shows a similar pattern. This element is particularly important because it forms in the cores of massive stars and gets expelled when they explode. Finding substantial carbon in early galaxies tells us that massive stars formed, lived, and died very quickly in the early universe. The carbon we see in these ancient galaxies came from stars that completed their entire life cycles in the first few 100 million years of cosmic history. Nitrogen presents a puzzle. This element forms through a different process than carbon or oxygen, requiring specific conditions inside certain types of stars. The fact that nitrogen appears early suggests that the universe had a diverse population of stars forming almost immediately after the first galaxies assembled. Not just massive giants, but a range of stellar types, each contributing different elements to the cosmic chemical inventory. Iron is especially interesting. This heavy element primarily comes from a specific type of supernova called a type Ia, where a white dwarf star in a binary system explodes. These explosions require time to set up, typically hundreds of millions of years. Finding iron in early galaxies pushes the boundaries of how quickly these systems could form. Either the early universe had ways of making iron faster than we understand, or the galaxies we're observing are slightly older than we think. The pattern emerging from Webb's observation suggests that star formation in the early universe was fundamentally different from what we see today. Stars formed faster, burned hotter, and died younger. The initial mass function, which describes how many stars of each size form, might have been skewed toward more massive stars. This would explain both the rapid element production and the intense brightness of early galaxies. Some computer simulations are now being adjusted to match these observations. By tweaking the conditions of early star formation, making stars form more efficiently or changing the mix of stellar masses, modelers can reproduce some of what Webb sees. But these adjustments come with trade-offs. Changes that explain one aspect of the observations often create problems elsewhere. It's a delicate balance, and scientists are still searching for a consistent model that explains everything. The search for population 3 stars continues. These primordial objects, if any still exist, would be incredibly faint after burning for over 13 billion years. More likely, they all died long ago. But their influence remains. The elements they created seeded the formation of every star and planet that came after. Finding direct evidence of these first stars would complete our picture of cosmic chemical evolution. Webb will keep searching, staring at tiny patches of sky for hundreds of hours, hoping to catch a glimpse of light from the earliest stellar generation. Even if individual population 3 stars remain hidden, their collective impact on galaxy formation and element production is becoming clear. They shape the universe we inhabit, transforming pure primordial gas into a cosmos rich with chemical diversity. As Webb maps the evolution of elements across cosmic time, measuring how oxygen, carbon, and other elements increased over billions of years, another mystery deepens. The very fabric of space itself seems to be expanding at different rates depending on how you measure it, creating a crisis in cosmology that Webb's data is making impossible to ignore. In 1929, an astronomer named Edwin Hubble made a discovery that changed everything we thought we knew about the cosmos. He noticed that distant galaxies were moving away from us, and the farther away they were, the faster they receded. This wasn't because galaxies were flying through space. Space itself was expanding, carrying galaxies along like raisins in rising bread dough. This discovery meant the universe had a beginning, that everything was once compressed into an incredibly hot, dense state that exploded outward in what we now call the Big Bang. Scientists wanted to measure exactly how fast the universe was expanding. This number, called the Hubble constant, tells us the rate at which space stretches. Knowing this value allows us to calculate the age of the universe, predict its future, and understand the forces governing cosmic evolution. For decades, astronomers worked to pin down this crucial number with ever-increasing precision. Here's where things get weird. There are two main ways to measure how fast the universe expands, and they give different answers. The discrepancy isn't small, isn't within the margin of error, and isn't going away no matter how carefully scientists check their work. This problem has become one of the biggest mysteries in modern cosmology. The first method looks at the universe when it was very young. About 380,000 years after the Big Bang, the cosmos had cooled enough for atoms to form. Before this moment, the universe was so hot that electrons couldn't stick to atomic nuclei. Free electrons scattered light in all directions, making the universe opaque like a thick fog. When atoms finally formed, light could suddenly travel freely. That ancient light still fills the universe today, stretched by expansion into microwaves. We call it the cosmic microwave background. This background radiation contains patterns, tiny variations in temperature from one region to another. These patterns formed when sound waves rippled through the early universe, creating regions of slightly different density. By measuring the size and distribution of these patterns, scientists can calculate how fast the universe was expanding back then. Using our best understanding of physics, they can project that expansion rate forward to today. This method gives a value of about 67 kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light-years, so this means that for every 3.3 million light-years of distance, space expands by 67 kilometers per second. The second method looks at the nearby universe. Astronomers identify certain types of stars and supernovas that have known brightnesses. By comparing how bright these objects appear to how bright they actually are, scientists can calculate their distance. Then they measure how fast these objects are moving away from us. Combining distance and speed gives the expansion rate. This method produces a value of about 73 kilometers per second per megaparsec. 6 kilometers per second might not sound like much, but it represents a 10% difference between the two measurements. In science, when two careful measurements of the same thing disagree by this much, something is seriously wrong. Either there's a mistake in one or both methods, or our understanding of how the universe works is incomplete. Scientists have spent years checking both approaches. They've looked for sources of error, recalibrated their instruments, tested different assumptions, and used independent measurements to verify their results. Both methods keep giving the same answers. The early universe measurement consistently yields 67. The nearby universe measurement consistently gives 73. The conflict isn't going away. This is where Webb enters the story. The telescope can see farther and more clearly than previous instruments, allowing it to make more precise measurements of distant objects. Webb has observed special variable stars called Cepheids, which pulse with a regular rhythm that reveals their true brightness. These stars serve as distance markers, helping calibrate the nearby universe measurements. Webb has also captured supernovas at various distances, providing additional data points for measuring expansion. The results from Webb haven't resolved the tension. Instead, they've confirmed that the discrepancy is real. The measurements are not wrong due to instrumental errors or bad assumptions. Both methods are genuinely measuring something different, which means our model of the universe must be missing something important. Several explanations have been proposed, each requiring new physics or modifications to our cosmic model. Maybe dark energy, the mysterious force driving accelerated expansion, doesn't remain constant over time. Perhaps it was stronger or weaker in the past, changing the expansion rate in ways we haven't accounted for. Current measurements suggest dark energy is remarkably steady, but maybe we're missing subtle variations that affect how we interpret the data. Another possibility involves dark matter, the invisible substance that makes up most of the matter in the universe. We know dark matter exists because we see its gravitational effects, but we don't know what it's made of or all its properties. Maybe dark matter interacts with itself in ways we haven't discovered, or perhaps there are multiple types of dark matter with different behaviors. These unknown properties could affect how the universe expands, creating the discrepancy between early and late measurements. Some physicists suggest the problem lies in how we understand the cosmic microwave background. The patterns in that ancient light depend on sound waves that traveled through the early universe. The speed of those sound waves depends on the density and composition of matter at that time. Perhaps there was an additional component, something we haven't identified, that affected sound speed and distorted our interpretation of the patterns. This hidden ingredient would change our calculation of the expansion rate from the early universe. A more radical idea involves questioning the fundamental cosmological principle that the universe looks the same in all directions. What if we live in a region where space happens to be expanding faster than average? This would make nearby galaxies appear to recede faster than they should based on the overall cosmic expansion. It's an uncomfortable idea because it places us in a special location, something scientists generally try to avoid. But Webb's ability to observe the universe at different distances might eventually test this hypothesis. The measurements Webb provides come from objects at intermediate distances, billions of light-years away but not as far back as the cosmic microwave background. These observations fill in the gap between early and late universe measurements. By tracking how expansion rate changes across cosmic time, scientists hope to identify when and why the discrepancy appears. Does the expansion rate change smoothly or are there jumps? Does something strange happen at a particular cosmic age? So far, Webb's data suggests the expansion rate has been remarkably steady, at least over the past several billion years. This rules out some of the wilder explanations involving rapid changes in dark energy or dramatic shifts in cosmic evolution. The mystery deepens because the measurements get more precise without getting closer to agreement. Some astronomers wonder if we need completely new physics to explain this tension. Maybe general relativity, Einstein's theory of gravity that has passed every test for over a century, breaks down at cosmic scales in ways we haven't yet detected. Perhaps there are forces or particles that only operate over distances of billions of light-years, too subtle to detect locally but significant over cosmic distances. The Hubble constant tension represents more than just a discrepancy between numbers. It suggests we're missing something fundamental about how the universe works. Every major breakthrough in physics has come from noticing something that didn't quite fit, some small anomaly that eventually revealed a deeper truth. The mismatch in expansion rate measurements might be telling us that the universe is stranger than our current theories allow. Webb continues gathering data, measuring distances to more objects, capturing light from different cosmic epochs, building a more complete picture of how expansion evolved over time. Each observation adds another piece to the puzzle. The telescope won't directly solve the mystery, no single instrument can, but it provides the high-quality data needed to test different explanations and rule out incorrect ideas. As scientists grapple with understanding why space expands at different rates depending on how you measure it, they face an even bigger question. Most of the energy in the universe comes from something we can't see, can't touch, and don't understand. This mysterious force makes up more than 2/3 of everything that exists, and it's tearing the cosmos apart faster and faster. Take everything you can see in the universe. Every star, every galaxy, every cloud of gas, every planet, every speck of dust floating in space. Add up all that matter. Now include all the dark matter, that invisible substance we detect through gravity but can't see directly. Combine everything, all the matter and energy contained in atoms and particles throughout the entire cosmos. You've just accounted for 32% of the universe. The other 68% consists of something we call dark energy, and we have almost no idea what it is. We know it exists because we can measure its effects. We know it's causing the universe to expand faster and faster. We know it seems to be spread evenly throughout all of space. Beyond that, dark energy remains one of the deepest mysteries in science. The story of dark energy begins in 1998. Two teams of astronomers were studying distant supernovas, massive stellar explosions that shine with predictable brightness. By measuring how bright these supernovas appeared and comparing that to how bright they should be, scientists could calculate their distances. These measurements would reveal how fast the universe was expanding at different times in its history. Everyone expected to find that expansion was slowing down. Gravity pulls everything together, so it should act as a brake on cosmic expansion. The question wasn't whether expansion was slowing, but how much. Would it slow enough to eventually reverse, causing everything to collapse back together? Or would it slow gradually but never quite stop, with the universe expanding forever at an ever-decreasing rate? The measurements showed something nobody anticipated. The expansion wasn't slowing down at all. It was speeding up. Distant supernovas appeared dimmer than expected, meaning they were farther away than they should be if expansion had been steady or slowing. Something was pushing the universe apart, working against gravity, causing galaxies to accelerate away from each other. This discovery stunned the scientific community. It won a Nobel Prize and immediately raised profound questions. What could possibly cause accelerating expansion? Where does this energy come from? Why does it act opposite to gravity, pushing instead of pulling? The simplest explanation involves something Einstein proposed a century ago, then abandoned as his greatest mistake. When Einstein developed general relativity, his equations predicted the universe should either expand or contract. At the time, everyone believed the cosmos was static and eternal. To make his equations produce a non-moving universe, Einstein added a term he called the cosmological constant. This represented an energy inherent to space itself, a sort of pressure that could counteract gravity. When observations later showed the universe was indeed expanding, Einstein removed the cosmological constant, calling it unnecessary. But the discovery of accelerating expansion brought it back. Maybe empty space really does contain energy. Maybe vacuum isn't truly empty but filled with a subtle field that creates outward pressure. This energy wouldn't clump or concentrate anywhere. It would be perfectly smooth, spread evenly throughout all of space. Here's what makes dark energy truly strange. As the universe expands, new space comes into existence. That new space brings new dark energy with it. The total amount of dark energy increases as the universe grows. More dark energy means faster expansion. Faster expansion creates even more space, which brings even more dark energy, accelerating expansion further. It's a feedback loop that drives the universe to expand faster and faster forever. This sounds like it violates one of the fundamental rules of physics. Energy should be conserved. You can't create it from nothing. But Einstein's general relativity allows for exceptions when space itself is expanding or contracting. The energy of the gravitational field can change, and in curved spacetime, energy conservation works differently than in flat space. Dark energy might be one manifestation of this strange behavior. Scientists want to know if dark energy is truly constant or whether it changes over time. A cosmological constant, by definition, never changes. The energy density of empty space would remain exactly the same throughout cosmic history. But dark energy could also be something more dynamic, a field that evolves and varies. If it's changing, the rate and pattern of that change would tell us what dark energy actually is. This is where Webb makes critical contributions. The telescope observes galaxies at different distances, meaning different times in cosmic history. By measuring how fast those galaxies are moving away from us and comparing measurements from different eras, scientists can track how dark energy behaved over billions of years. Has its strength remained steady? Has it grown stronger or weaker? Are there any patterns or variations? Current measurements from Webb and other telescopes suggest dark energy has been remarkably stable. Its density appears essentially constant, matching the simplest theoretical model. But these measurements have limits. Detecting small changes in dark energy requires extremely precise observations across many cosmic epochs. Webb is gathering that data, slowly building a complete picture of dark energy evolution from the early universe to today. The constancy of dark energy, if confirmed, raises troubling questions. Why does it have the specific value we measure? The amount of dark energy in the universe appears finely tuned. A little more, and galaxies would never have formed because space would expand too fast for gravity to pull matter together. A little less, and we'd see different cosmic evolution. The observed value seems carefully balanced, which makes physicists uncomfortable. Nature doesn't usually produce special numbers without reason. Alternative theories propose that dark energy isn't a property of space but rather a new kind of field permeating the universe. These models, grouped under the name quintessence, allow dark energy to change over time. The field could be stronger in the past or might grow stronger in the future. Different versions predict different behaviors, giving scientists multiple hypotheses to test. Testing these ideas requires looking at how the universe evolved. Webb observes distant galaxies forming when the cosmos was younger. By measuring their distances and motions precisely, astronomers can determine whether expansion was accelerating at the same rate back then as it is now. Any deviation from constant acceleration would indicate that dark energy is dynamic rather than constant. The future of the universe depends entirely on what dark energy does. If it remains constant, as current measurements suggest, the cosmos will continue accelerating forever. Galaxies outside our local group will eventually recede so fast that their light can never reach us. They'll disappear beyond a cosmic horizon, forever unreachable. The universe will grow darker and emptier as stars burn out and die without being replaced. Over trillions of years, even the largest structures will dissolve as dark energy pulls them apart. The Milky Way and nearby galaxies will merge into one massive galaxy, but beyond that island, the universe will appear completely black. Eventually, even the stars in that merged galaxy will die. The cosmos will become cold, dark, and essentially dead, continuing to expand into infinite emptiness. But if dark energy increases over time, things could get much stranger. Accelerating expansion might become so extreme that it tears apart not just galaxy clusters, but individual galaxies, then solar systems, then planets, and eventually atoms themselves. This scenario, called the Big Rip, would see the fundamental fabric of matter destroyed as space expands faster than the forces holding particles together. Current measurements show no sign this will happen, but we can't rule it out completely. On the other hand, if dark energy decreases or somehow reverses, expansion might eventually slow and stop. Gravity would then take over, pulling everything back together in a big crunch. The universe would collapse to a singularity, possibly followed by another Big Bang in an endless cycle. This scenario also seems unlikely based on current data, but remains theoretically possible. Webb's observations of distant supernovas and galaxies provide crucial data points for testing these scenarios. Each measurement helps constrain the properties of dark energy, ruling out some models while supporting others. The telescope doesn't just take pretty pictures. Every photon it captures carries information about the fundamental forces shaping cosmic destiny. Some scientists wonder if dark energy is telling us that general relativity breaks down at cosmic scales. Maybe gravity works differently over billions of light years than it does in our solar system. Perhaps there are modifications to Einstein's equations that become important only when dealing with the entire universe. These theories, called modified gravity, attempt to explain accelerating expansion without invoking dark energy at all. Testing modified gravity requires comparing predictions to observations across many different measurements. Webb contributes by providing precise distances to objects throughout cosmic history. If gravity behaves oddly at cosmic scales, we should see specific patterns in how galaxies move and how light bends around massive objects. So far, general relativity passes every test, but scientists keep looking for deviations. The mystery of dark energy represents one of the great intellectual challenges of our time. We live in a universe dominated by something we don't understand. It shapes the past, controls the present, and determines the future of everything that exists. Webb stares into the depths of space and time, gathering clues about this invisible force, trying to reveal the nature of the energy that fills the cosmos. Yet for all its power, even Webb has limits. There are places it cannot see, times it cannot reach, mysteries that remain just beyond its grasp. Webb is the most powerful telescope ever built. Its mirror collects more light than any previous space telescope. Its infrared sensors are the most sensitive ever launched. Its position beyond Earth's atmosphere gives it a view unobstructed by air or weather. Yet despite all these advantages, there are fundamental limits to what Webb can see. Some objects are simply too faint, too distant, or emit light at wavelengths the telescope cannot detect. The first 200 million years after the Big Bang remain largely hidden, hovering just beyond Webb's reach. Galaxies from this earliest epoch would have extremely high redshift values, above 20 on the astronomical scale. Their light has been stretched so far into the infrared that even Webb's specialized sensors struggle to detect them. The photons have been traveling for so long, stretched by so much cosmic expansion, that they arrive at the telescope as faint whispers of their original energy. These earliest galaxies would also be physically small. They had less time to grow, less gas to form stars, less material to work with. Computer simulations predicted the first galaxies would have masses of just a few million times the Sun, compared to hundreds of billions of solar masses in large modern galaxies like the Milky Way. An object this small and dim, even magnified by gravitational lensing, would be nearly impossible to detect without exposure times longer than Webb's mission lifetime. But here's where things get interesting. Every prediction about early galaxies has been wrong so far. Scientists expected small, dim, simple structures. Webb found large, bright, organized galaxies. The trend of galaxies being more luminous than expected continues as we look back further in time. Perhaps this pattern extends all the way to the beginning. Maybe galaxies at redshift 20 are brighter than models predict. If so, Webb might actually be able to see them. The telescope has the technical capability to detect galaxies at these extreme distances if they're bright enough. Each deep observation Webb conducts, staring at tiny patches of sky for hundreds of hours, pushes the boundaries. Astronomers keep finding galaxies at greater and greater distances. The record keeps getting broken. Each new discovery suggests that maybe, just maybe, Webb will glimpse something from those first 200 million years. The challenge isn't just distance. At extreme redshifts, distinguishing real galaxies from other objects becomes difficult. Certain types of cool stars in our own galaxy can mimic the colors of the most distant galaxies. These nearby imposters appear red because they're cool, not because their light has been stretched by cosmic expansion. The only way to tell them apart is through spectroscopy, splitting light into its component wavelengths to identify characteristic patterns. Getting spectra of the faintest objects requires enormous amounts of telescope time. Webb must stare at a single target for tens or even hundreds of hours to collect enough photons for analysis. The telescope has a limited lifetime, perhaps 10 to 20 years depending on fuel reserves and instrument health. Scientists must carefully choose which objects deserve this investment of precious observing time. Webb will continue pushing deeper. Each year brings improvements in data analysis techniques. Astronomers develop better ways to extract faint signals from noisy data. They learn to use gravitational lensing more effectively, searching behind massive galaxy clusters where spacetime curves enough to magnify distant objects. They identify promising candidates more efficiently, focusing Webb's attention on the most likely targets for breaking distance records. The telescope's mission could extend well beyond its designed lifetime. Hubble was supposed to operate for 15 years. It lasted more than 30. Webb's fuel supply determines how long it can maintain its orbit at the Lagrange point. Engineers built in generous margins. If nothing breaks, Webb might keep observing for 2 decades or more. Every additional year brings hundreds of hours of potential observations, thousands of new discoveries, countless opportunities to peer deeper into cosmic history. But eventually, Webb will reach the absolute limits of what's possible with a mirror its size and sensors of its sensitivity. The most distant galaxies will remain hidden, their light too faint to capture. The very first stars, if any still exist, will stay invisible. Future generations of telescopes will be needed to see what Webb cannot. Plans for these next-generation instruments are already being developed. Concepts include telescopes with mirrors twice the diameter of Webb's, collecting 4 times as much light. Others propose arrays of multiple telescopes working together, combining their light to create even greater sensitivity. These facilities would extend observations to redshift 25 or beyond, potentially imaging the very first stars that ignited in the cosmic dawn. But these future telescopes won't launch for decades. They require technologies not yet developed, budgets not yet approved, international collaborations not yet formed. The political and financial challenges of building something more ambitious than Webb are immense. It took 20 years to build Webb. The next generation might take just as long, or longer. Ground-based telescopes also play a role. New facilities with enormous mirrors are under construction on mountaintops around the world. These will have greater light-collecting power than Webb in some wavelengths. However, Earth's atmosphere absorbs most infrared light, severely limiting ground-based infrared astronomy. For observing the most distant galaxies, space telescopes remain essential. The atmosphere creates another problem. Air turbulence blurs images, making stars twinkle and smearing out fine details. Modern telescopes use adaptive optics, deformable mirrors that adjust hundreds of times per second to counteract atmospheric distortion. These systems work remarkably well for bright objects. But for the faintest, most distant galaxies, nothing beats the steady, clear view from space. Webb represents the frontier of what's possible with current technology. Every observation pushes the boundaries of detection. Every deep exposure reveals objects at the edge of visibility. Scientists analyze each image pixel by pixel, searching for faint smudges that might be distant galaxies. Sometimes they find nothing. Sometimes they discover something that changes our understanding of cosmic history. The telescope has already transformed our view of the early universe. Black holes too massive for their galaxies. Galaxies too bright for their age. Stars forming faster than theory predicts. Structures emerging earlier than thought possible. These discoveries don't break cosmology. They expand it. Our models were too simple, our predictions too conservative. The universe is richer and more complex than we imagined. Webb shows us reality, and our theories must adapt to match. This is how science progresses. We build instruments to test our ideas. When observations match predictions, we gain confidence. When they don't, we learn something profound. Webb's observations of the early universe tell us that the story of cosmic evolution has more chapters, more plot twists, more surprises than we anticipated. The telescope will continue its mission for years to come. Each week brings new observations. Each month produces new discoveries. Astronomers around the world compete for time on Webb, proposing observations they believe will answer fundamental questions. A committee reviews thousands of proposals, selecting the most scientifically valuable. The chosen programs observe everything from nearby planets to the most distant galaxies, from dying stars to forming solar systems. Webb has uncovered the true scale of the universe, revealing it to be vaster, stranger, and more magnificent than anyone predicted. Galaxies assemble faster than we thought. Black holes grow larger than they should. Elements form earlier than expected. The cosmos refuses to fit neatly into our theories. It continually surprises us, challenging everything we think we understand. This is not a problem. This is thrilling. Every unexpected discovery opens new avenues of research. Every violation of our predictions teaches us something about the actual universe, not the simplified models we've built. Webb has become a machine for generating questions as much as answers. It shows us what we don't know, pointing toward the mysteries that future generations will solve. The data flowing from Webb will keep scientists busy for decades. Even after the telescope eventually falls silent, researchers will analyze its images, finding new details in observations made years or decades earlier. The full scientific value of Webb won't be realized until long after its mission ends. Future astronomers will look back at Webb's discoveries the way we now look at Hubble's, as the beginning of a new era in understanding the cosmos. As Webb continues its vigil in the darkness, staring at the edge of time itself, we stand at a unique moment in human history. We are the first generation capable of seeing the universe as it truly is, the first to witness the birth of galaxies, the first to measure the age and fate of all reality. We are living through something extraordinary, a moment that future generations will look back on with envy. For all of human history, people stared at the night sky and wondered. They created myths to explain the stars. They built theories about the cosmos. They argued about whether the universe had a beginning or had always existed. But they could never truly see beyond the limits of their own eyes, beyond the tiny fraction of cosmic history visible from Earth. That changed in our lifetime. We have built machines that can look back through time, capturing light that began its journey when the universe was a newborn. We can watch galaxies forming in the cosmic dawn. We can measure the age of reality itself. We can trace the evolution of matter from simple hydrogen gas to the complex chemistry that makes life possible. This is not normal. This is not something every generation gets to experience. We are witnessing the universe reveal its deepest secrets, and Webb is our window into that revelation. Every discovery Webb makes challenges something we thought we understood. The massive galaxies that formed too quickly force us to reconsider how gravity assembles cosmic structures. The oversized black holes that violate every rule require us to rethink the very first moments after the Big Bang, searching for processes that could birth these monsters. The rapid appearance of heavy elements tells us that stellar evolution in the early universe operated under different rules, perhaps more violently, certainly more efficiently than modern star formation. The contradiction in expansion rate measurements points toward physics we haven't discovered yet. Either dark energy behaves in ways we don't understand, or gravity operates differently at cosmic scales, or space itself has properties we've never detected. One of these must be true because the measurements don't lie. The universe is telling us something important, whispering clues about its fundamental nature. We just have to listen carefully enough to hear the message. Dark energy remains the greatest mystery. More than 2/3 of everything that exists consists of something we cannot see, cannot touch, cannot explain. It fills the vacuum of space. It pushes galaxies apart. It determines whether the universe will expand forever or eventually collapse. We have measured its effects with incredible precision, but we still don't know what it actually is. Future discoveries might reveal dark energy to be something simple and elegant, or they might show it's far stranger than we imagine. Webb has rewritten the early chapters of cosmic history, but the book is far from finished. The telescope will continue observing for years, perhaps decades. Each observation adds another piece to the puzzle. Some pieces fit together easily, confirming what we suspected. Others don't fit at all, forcing us to rethink the entire picture. The discoveries that surprise us the most are often the ones that teach us the deepest lessons. The data Webb collects today will be analyzed for generations. Young scientists just starting their careers will spend decades studying these observations, extracting insights that weren't obvious at first glance. Images that seem ordinary now might contain hidden galaxies waiting to be discovered by better analysis techniques. Spectra that appear confusing today might make perfect sense once we understand the physics better. Webb's true legacy won't be measured in years but in centuries of scientific progress built on its observations. We stand at the threshold of understanding. The universe has existed for nearly 14 billion years, but only in the last few years have we developed the technology to see it clearly. Only now can we look back to when galaxies were forming, when the first stars ignited, when the cosmic web began to take shape. We are the first humans to witness these events, to see the universe as it actually was rather than how we imagined it to be. The cosmos waited patiently through billions of years of evolution, through the formation of our sun and planets, through the rise of life on Earth, through millions of years of human evolution, waiting for the moment when our species would develop the technology and curiosity to look back and see where everything came from. That moment is now. We are the generation that gets to see cosmic dawn, to watch the universe wake up and come alive with light. Webb has shown us that the universe is more dynamic, more violent, more creative than we gave it credit for. Things happened faster in the early cosmos. Structures assembled more quickly. Stars formed more efficiently. Black holes grew more rapidly. The universe was in a hurry to create complexity, rushing through processes we thought would take billions of years. Why this rush? We don't know yet. But the fact that it happened tells us something profound about the conditions of the early universe, about forces and processes we're only beginning to understand. Every week, new papers are published based on Webb's observations. Every month brings fresh discoveries that make headlines. Astronomers around the world are racing to analyze the data, to extract every bit of information from each observation. The pace of discovery is accelerating. We're not just learning new facts. We're developing entirely new ways of thinking about how the universe works. The story Webb is telling us is not the one we expected to hear. We thought we understood the basic plot. The universe begins with the Big Bang, matter slowly clumps together under gravity, stars form, galaxies assemble, everything proceeds in an orderly fashion over billions of years. But the real story is messier, faster, more chaotic, and infinitely more interesting. The universe didn't follow our script. It improvised, taking shortcuts, finding faster paths to complexity, violating the rules we thought were inviolable. This is how science moves forward. We create models based on limited data. Those models make predictions. Then we build better instruments to test those predictions. When the predictions fail, when reality doesn't match our expectations, we don't despair. We get excited. We know we're about to learn something new, something fundamental. The observations that confuse us the most are pointing toward the biggest breakthroughs. Webb is not just a telescope. It's a time machine, a history book, and a crystal ball all rolled into one. It shows us where we came from by revealing the universe's infancy. It explains how the matter in our bodies was forged in stellar furnaces billions of years ago. It hints at where everything is heading, toward an ever-expanding future dominated by dark energy. We are made of stardust, and Webb shows us the stars that made us. The cosmos has always been there, vast and magnificent, waiting to be discovered. For thousands of generations, humans looked up and wondered. Now, finally, we have the tools to answer some of those ancient questions. Where did we come from? How old is everything? What came before? The answers are appearing in the data Webb sends back, in the light from galaxies that formed when the universe was learning to be a universe. This is only the beginning. Webb has opened a door that cannot be closed. We have seen what lies beyond, glimpsed the cosmic dawn, witnessed the birth of galaxies. Future telescopes will push even deeper, seeing things Webb cannot. But this moment, right now, when we first truly saw the early universe, will be remembered as a turning point in human history. We are the generation that looked back to the beginning of time and finally understood what we were seeing. The universe waited 13.8 billion years to be discovered. Now we are looking back to the very edge of time itself, watching the cosmic story unfold, seeing the universe as it truly is rather than how we imagined it to be. Every observation Webb makes is a gift, a glimpse into depths of space and time that were forever hidden until now. We are incredibly fortunate to be alive at this moment, to witness these discoveries, to see the cosmos reveal its secrets. The journey has just begun. The best discoveries might still be ahead. And Webb will keep watching, keep observing, keep showing us wonders we haven't yet imagined. The universe is vast beyond comprehension, strange beyond imagination, and more beautiful than any human creation. Webb is our guide into that immensity, our torch in the cosmic darkness, our window into infinity. Welcome to the golden age of astronomy. Welcome to a time when the impossible becomes visible, when ancient light finally reaches our eyes, when the secrets of creation itself are revealed. The universe has stories to tell, and we are finally ready to listen.